And then we're going to practice it in context. Okay, so here it goes. What that thing p-value is that you were dealing with yesterday means this. It is actually the probability. So if you look at a curve, it's that shaded area. The probability that you get that particular sample that you got, or something more extreme. Well, something more extreme means going out to infinity, whether you're going out to positive infinity if it's an upper tail, or negative infinity if it's a lower tail. Something more extreme. If the null hypothesis is true. The concept of this null hypothesis being true happens because of this. So let's draw two pictures here. One is going to be a single tail and one is going to be a two-tail. So what's happening is we're going to, when we dive into a problem and you say normal model applies, you are going with the idea that this normal model is built around your null hypothesis being there in the middle. Okay, so if that null hypothesis is true, then here's all that's happening around it. So if, say, this is a alternative that's a greater than problem, then you have an upper tail. Say you get a sample way up here, way high. Then the p-value is this probability. So look here at the picture how this works. It's the probability of getting this sample or something more extreme. So probability is the size of this shaded area. So that is what the p-value is if you were to look at it in a concrete picture. Okay? So over here, if we have a two-tail, two-tail is going to happen when you have a not equal to problem. That means anything way high or way low causes you to reject the null. So what happens is, if in the problem you are doing, you got a sample that was a way high sample, you would get something like this. And of course, your p-value is getting something where at your sample or something more extreme. Okay? But on this type of problem, since this is two-tail, when you find your sample or something more extreme, you mirror image it over here. So essentially, you take, to get the total p-value, to get the total p-value, you essentially take one tail's p-value, and you multiply that by 2 to get the total p-value. Okay. So now, let's talk about this next thing that we've referenced. You know, we kind of went through the test, and we did all of that, and we were just throwing out these things like p-value and alpha. Let's just make sure we really have that solidified. So alpha, which we represent with this symbol here, is basically the threshold of the rejection region that is happening. So it has to do with that size of the rejection region. Okay, so for example, if, say, on this problem, I tell you that the alpha is 0.05, and that ends up being here, which puts my rejection region like that, then let's discuss this. Number one, tell me the location. Tell me about the location of my sample. My sample is located, what? In the rejection region. This p hat is located in the red. So this p hat is in the rejection region. So then, according to this picture, what decision would be made? To reject the null. Okay, good. Here's another way of thinking about this. You see, look at the size of this p-value, which is in green. Compare this size of this p-value to the size of the entire alpha. What is the relationship between those two? The p-value is actually what? Smaller than alpha. And see, if the p-value is low, the null has to go. Because if the p-value is lower than alpha, that is because your sample is in the rejection region. I'm going to say that one more time. If your p-value is a smaller p-value than the entire alpha rejection region, then that is saying that your sample is in the rejection region. That is why if the p-value is low, the null has to go. Okay, good. Well, let me ask you this. What happens if, say, on this picture over here, we get an alpha such as this, which the mirror image would put the other part here. So our alpha is split between the two tails. In a case like this, would we end up rejecting? No. Very good. We are not rejecting because my red rejection region is what in relationship to the p-value? It is smaller. The red is smaller, the p-value is greater, okay? And can you see where the sample is? See this p-hat? See how it is not in the rejection region? Hence, another, confirmation as to why you do not reject if your p-value is larger than your alpha. Okay, so that's what's happening. So that's the very fundamental, concrete manner of what is going on. So now, let's put these things into works with actually doing some context. So here we go. In a 2001 National Vital Statistics report, it was indicated that about 3% of all births produce twins. Okay, so we have the rate of all births. Data from a large city hospital found that 7 sets of twins were born to 469 teenagers. Question, what do you think this thing is going if it sections off a subgroup of just teenagers and the proportion of twins in there? That's going to be your p-hat. So what do they think they're wondering in this problem? Good. Yeah. If you are a teenage girl, and I don't think they even say more likely or less likely, is the rate at which you have twins different from the rate, if you are a teenage girl versus all births? So that's kind of where we're headed with this. All right. So running an appropriate hypothesis test provided a p-value of 0.028. Explain what this p-value means. So here's what you have to do. You don't have to write this down, but you have to think it. And I don't like keeping things in my head. I'm not just a float around in my head type person. I like to write it down because I want to see it. I am thinking, I have to think what the null hypothesis is. And so here, P is the proportion of teenage girls that have twins. And we're going to be seeing if that is the same as the overall twin birth rate. So what is the null hypothesis here? That P equals 0.03. We first start off saying the twin birth rate among teenage girls is the same as overall. Now let's see if we have evidence to reject that. See? So my alternative, I don't have any indication if I know it's way more or way less. So I'm going to put a not equal to here. Because I'm just going to take data and see where it falls. I'm not hypothesizing that it's way less or anything or way more. So this is not something you require. This is something that your brain has to think from the get-go. All right, here we go. So let's do this p-value. Now, for this first one, I want to have us actually look at this definition as I say it in words, okay? So I would say this. By the way, the p-value on that was 0.028. So I would start off saying, there is a 0.02 or 2.8% chance of getting the sample that we got, which was 7 out of 469, or something more extreme if the proportion of teenage girls that have twins is 3%. So let me say that again. Let me walk you through this definition one more time with the words, and then we'll write it down. This problem in context says there's a 2.8% chance of getting the sample that we got, which was 7 out of 469, or something more extreme. That means something to the higher than or to the lower than, whichever way it goes. If the null hypothesis, which is the proportion of teenage girls that have twins, is 3%. Boom, and that's done. So let's explain what the p-value means in context. So here we go. There is a 2.8% chance that I got this sample result. Actually, I'm just going to say sample, and then I'm going to say in parentheses 7 out of 469. Or what? Something more extreme. That's actually important because that makes the area. That makes the tail. That's like going out to infinity. If you don't have that, then you don't have an area. Or something more extreme. All right. If the null hypothesis is true, so what am I gonna do for the null hypothesis is true? If the proportion of teenage girls that have twins is 3%. So that is what the p-value means. It means your sample's out there. Here's a picture of it. Here is 3% of teenage girls having twins. But you get this 7 over 469. I don't even know what that is. Is that way small or way big? So 7 over 469. It's smaller. So we got something way down here. And so that means that the chance of getting that sample or something more extreme is 2.8%. This is a 2.8% chance. 2.8% of samples fall down there. Okay? All right, so now let's actually work on this first page of your homework together. So pull out this page right here. You're going to do all of these. So we're just on a roll. You're going to be getting this stuff done. Okay, here we go. First thing I want you to think as we are going through here is what is this problem about, and what is my null and alternative going to probably be? So here we go. A medical researcher has tested a new treatment for poison ivy and compared it to the traditional ointment, the old treatment. So with a p-value of 0.047, he concludes that the new treatment is working, is more effective. Explain what that p-value means in this context. So, what's happening in this problem? And it's experiment to do what? Compare two treatments. The what to the what? New treatment to the old treatment. So we're not gonna say, and this is different than you've ever done before, but we're gonna kind of just think about this way. The null is going to be something like the proportion or whatever that's with the new treatment is the same as the old treatment. We start off saying nothing is happening. They are equal in their effectiveness because the null is always the equal to. Now, the alternative that would happen is that what? Whatever proportion or whatever measurement it is for the new treatment is better, so more effective. Okay, so that's what's happening. So let's do this thing here. So tell me how we're going to start out with a p-value of 0.047. There's a 4.7% chance that we got our sample results. See, we don't actually have details about what that sample is, so we just have to put sample results. Or what? Something more extreme. If the null hypothesis is true, so what am I going to write for the null hypothesis is true? The new treatment is as effective as the old treatment. Good. If the new treatment is as effective, I think it's an A, as the old treatment. Oh, okay. Yeah, I guess it's the effect that it's doing. So that's a noun. Okay, very good. Good, good, good. Okay. So I bet you this one is going to fall even easier for you. So let's do this next one here. The question starts off wondering if harsher penalties and ad campaigns have increased seatbelt use among drivers and passengers. Okay. Before I even get into this, I want to flash back to the beginning of the year. This is not going to be an imposed treatment where you like make some people wear seatbelts or make some people look at ad campaigns and some people not. This is not going to be an experiment design. We can't make a cause and effect conclusion. We're just going to be able to, it's a study, so we can't do a cause and effect. So in essence, where I'm going with this is, you do not have the right to reference this or this as a quote-unquote cause. Okay? So your problem, what is your job as a statistician? You are collecting data, and your job as a statistician is to compare what? They're talking about seatbelt use now and seatbelt use 3 years ago. So your job, the comparisons you're going to be making is probably the proportion of people that you see among the drivers and passengers that you see if they are wearing their seatbelt or not. Okay, so let me finish reading this so that I'm kind of talking to you about it before fully reading it. So, have those harsher penalties and ad campaigns increased seatbelt use among drivers? You have no right to make that conclusion. And passengers. Observations of commuter traffic failed to find evidence of a significant change compared with 3 years ago. Explain what the study's p-value of 0.17 means in this context. So, first of all, if you are a statistician and you're comparing things, what are you going to be comparing? Then to now. Then to now. So you're going to be comparing the proportion, 3 years ago to the proportion today. The proportion of seatbelt wearers, I guess. Proportion of drivers and passengers that are wearing their seatbelt. Okay? So mathematically, that's what you as a statistician are going to do. And the hope is that, of course, harsher penalties and ad campaigns have done what? So the alternative, in a sense, is going to be that the proportion of seatbelt wearers 3 years ago is less than today. Okay, so there's what's going on with this problem. So let's now line this up. We got a p-value of 0.17, so that means that there is a 17% chance of getting our sample results something more extreme if what? Okay, I'm going to try and make this as short as possible. The seatbelt rate 3 years ago is the same as today. I think that's probably as easily as you can write that. Okay, good. Hey, do you get why you can't say the ad campaign? Remember, so you can't do that. You can't say, oh, it's because of harsher penalties or whatever. Oh, by the way, why do you think with a p-value of 0.17 you would fail to reject? Because that 0.17 is probably greater than the default alpha, which the default alpha is 0.05. Okay, so that's probably why it failed to find evidence. Okay. All right. Now, number 3 actually is quite a bit different from those other two. 4 is the same, so I'm going to have you do that one here in a minute. But let's talk about number 3. It's a very important thing to understand. Where what we are talking about with this one is the effectiveness of the scanners for hidden weapons at airports. And there's a new device that they are saying is significantly better than the current device. Okay. This key, significantly better, is implying that the null hypothesis was rejected. And it was found significantly better. He made this decision based on an alpha of 0.05. Okay. So let's think of this problem. So we're comparing the what? So the null is that the new device works the same as the old device. Okay, the alternative is that the new device works better than the old device. Okay, so that's what's happening. So this is not actually just asking you to interpret the p-value, so I want to draw a picture to demonstrate what this is about. This is a normal model if the null hypothesis is true, if the devices work the same. Well, this guy found a sample where the new is significantly better. So that means he had a sample way up here. It's significantly better, okay? All right. And he made this decision based on an alpha of 0.05. That means that with an alpha of 0.05, he did what? With the null. He rejected it. Very good. So with an alpha of 0.05, he rejected. That means that alpha must be, somewhere here. The sample must fall in the rejection region. Got that? Because they tell us that he rejected the null at 0.05. Okay. Next question is this. Would he have made the same decision at a different alpha? This alpha of 10%. So I want to know what on this picture would an alpha of 10% look like? It's actually bigger. So where would my line be? Yeah, more left. So here would be an alpha of 10%. See how much bigger this region is? So question, at an alpha of 10%, what decision would have been made? You would still reject. Because do you see that that sample is still in the rejection region? Here it is. It is in the red rejection. It's definitely in the black rejection region. Okay. But the last question is, how about a rejection region of just 0.01, an alpha of 0.01? What about that? We don't know. Could be smaller, could be less. I don't know if 0.01 falls here, or I don't know if 0.01 falls here. Okay, but, so So 0.01 could have the rejection region in it, or it might not. If it's just right here, then it would not have that in there. Okay, so now I've messed up all my coloring. But here's my p hat. If that 0.01 is here, then it does not contain that sample and you don't reject. So with an alpha of 0.01, your decision is what? Unknown. You do not necessarily reject. Okay? All right. So he rejected at the 0.05, then he definitely rejected at the 0.10. But he did not necessarily reject at the 0.01. Okay, very good. Now, number 4 is something that I think you can do. So I'm going to pause for a minute and let you have a chance to do that one. So go. Out. What does this P stand for that I have written here? Good. The proportion of children that got vaccinated against measles. Okay, good. So with a p-value of 0.011, there is a what? 1%, 1.1% chance. Okay, that we get these sample results. Yeah, you know, if you want to, it's not required, but it defines for us what those sample results are. So if you had put in this, because that's the sample results they got, you're good. That we got that, or something more extreme. If what? Good. The proportion of children vaccinated against measles is, sorry, I'm writing this really sloppy because I'm trying to go fast since you've already written this down, is 90%. Okay, now I actually want to ask an extension question. Yes, go ahead.
We put the actual sample result. Do we have to, so I wrote, there's a 1.1% chance of getting only 89.4% of 13,000 children vaccinated against measles.
Or something more extreme, and then that would be correct. Yep. So that's a good question. If you just used this instead of saying sample results, that's fine. Those are interchangeable because the 89.4% is the sample results. Okay?
You don't have to put,
You don't have to put both.
you don't have to put out of 3,000 either.
Oh, out of 13,000. I think that this 13,000 actually plays more into the p-value issue. Because this is in a percentage, then that's universal to regardless of your sample size. So I don't think the 13,000 is necessary. If you had put it, no problem.
That could mean like 89% of the whole population.
0.4% of whatever size sample you had, because it's a sample. Whatever size sample, 89.4% of whatever size sample. Okay. Now, but here's my extension question. Okay, you ready? Alpha of 0.05. Reject or fail to reject? Question. Why reject? Good. Because a p-value of 1.1% is less than 5%. Okay. All right. Next question. Alpha of 0.10. Reject or fail to reject? We reject. Why? Because it's still lower, p-value is still lower than alpha. Okay. This is 0.011. All right. Alpha of 0.011. What do you do there? fail to reject because in that case, your p-value is not smaller than this alpha. Okay? You would not be given an equal to. If they are equal to, I think probably you're going to have to check again because you have inconclusive evidence. Okay, good job. Now, back to your notes. We're going to, last thing is clarify how do you do a phantoms model with a two-tail problem. So this is the back of the notes. And the first thing I want you to do is notice, look at this piece of paper. It is all completely blank. You have no what here on this paper? You have no chart to guide you through. So you had that chart yesterday. That was your little baby step process. And now you have to start internalizing that. Okay, so let's do this. Here we go. The packaging on a deck of random baseball cards states that the proportion of all-star players in the package is 20%. Now, one little detail that I have to fix, and I realized this during second period because I made this problem yesterday. This is not what I intended this problem to be about. I did not mean for this to be 20% of the all-star players are going to be in your package. I meant that 20% of the deck is going to be all-star players. See? This is subtle. So let me write the correction and then we'll compare it. You have to get this. So the proportion of the deck, or the baseball cards, deck of cards that are all-star players is 20%. What is the difference in these two statements? Proportion of the deck versus proportion of the all-star players. What's going to be the mathematical difference? The denominator of the fraction. Okay, so I intended that upper one. We're talking about the proportion of the deck. That's all-star players. So here we go. The company plans to test this hypothesis to see if that approximation is valid. Due to contract agreement with MLB Players Union, the company does not want there to be too many all-star player cards in the deck. And for legal purposes, the company does not want there to be too few all-star player cards. Okay. A random package of 50 cards ends up having 14 all-star players in the package. So does this lead the company to reevaluate the process by which it distributes baseball cards? Okay. So we will start our model with what? P. P is the population parameter. So what is the population parameter? Aha. Proportion of the deck that is all-star players. Good, because that's correct. Okay. What does the H mean in our phantoms model to do? What does that remind you to do? Your hypothesis statements. So the null hypothesis is that P, what? Is 0.20. And the alternative is what? Not equal to. Way high and way low would cause us to reject this 0.20. Okay? Way high and way low are both bad things that would cause us to reject. Okay. What is next in our phantoms model? A stands for assumptions and conditions. Okay, so you write those down. You know them all, so I'm going to write those down here real quick. Go. Okay. Ta-da! So that's exactly what yours should look like. Okay, make sure you use the true P here. Okay, true P right here. Okay, all right. So next is what? And what does that tell you to do? Okay, name the test, which is a one proportion Z test. Our old thing was a one proportion Z interval. Okay, phantoms. So to T. What does T mean? Test statistic. That is our Z-score. Later we're going to have different things other than Z-scores, but our test statistic, all that we know now is a Z-score. You don't have to write this, but just by the way, here's the formula for that. So, the p-hat is what? Good, that's your point 28 because it's 14 out of 50. And the standard deviation of your p-hat, this is so tempting to want to put 0.28 in there because you just wrote 0.28, but don't. What's in there? 0.2. I was looking at an answer key of mine last night, and I had whiteout on it because on several of them, I had put the p-hat here instead of the true P. So see, that was a common thing I had fallen for when I wasn't keen to watch for that. That is 0.0566. So, you better write Z equals, and then your thing here. That is 1.41. It's positive. So, question, on this tail, which way would be more extreme? Positive. Okay, so here's what's happening. Here's the null. We are we have a sample right here. Okay? So, a p-value is going to be this probability of getting this sample or something more extreme. This is one tail. So, the upper tail is going to be, how do I get this here? Norm CDF from 1.41 to infinity, and I'm going to tell you that's 0.0793. Okay, but guess what, people? This is not the entirety of your p-value since this is two-tail. It's the only thing that's special about two-tail. The fact that it's two-tail means that we also have the symmetrical aspect as part of the p-value. So the p-value in its entirety is actually that amount times 2. Okay? Because you just found one upper tail, and so then you would say, well, then the total p-value is going to be 0.159. Okay? You are only multiplying this by 2 because this is a two-tail problem. If all this was a greater than problem, you'd be 0.0793. Okay, what is next in our phantoms model? After the T comes O. What does O mean? O means obtain a p-value. Well, we just did. So my p-value equals 0.159. There is not a defined alpha, so my default is 0.05. And what is the connection between those two? The p-value is larger than my alpha. So M means make a decision. So my decision is to fail to reject because the p-value is not low. So the null does not go. Fail to reject. And then you're going to state your conclusion, and that's nice that that's an S because that reminds you to say, since the p-value is greater than alpha, I fail to reject that. Here comes context. What's my context? The proportion proportion of the day. That is all star players is 20%. Okay, so I don't reject that. And then final question is, I'm reading from the problem. Does this lead the company to reevaluate the process by which it distributes baseball cards? Do they need to reevaluate their process? No, we do not have, and here is actually going to make you sound so statistically smart. This is a catchphrase that just like really clicks. We do have evidence to suggest, or we do not have evidence to suggest. Evidence to suggest is what we have in our sample. And so, I mean, that's what you're looking for. So, for this situation, did our sample give us evidence to tell them to reevaluate the process, or does our sample not give us evidence to tell them to reevaluate their thing? Does not. Very good. So therefore, we do not have evidence to suggest, it's going to be your common catchphrase, to suggest that the company needs to reevaluate its process. Ta-da! Very good. Now, we're done with notes, and your first thing that you're going to do in these last 10 minutes of class is this James Bond problem. So it's actually got something that's difficult to understand, so let's do it together so I make sure you understand why this is two-tailed. Okay, so here we go. The problem number 5 on your homework is about James Bond. And you know, when he has his martini in all his movies, what always is it? Shaken, not stirred. So the question here is, does he really have the appropriate skills to determine if his martini is shaken and not stirred? Or can he tell the difference between shaken and stirred? So that's the question. So this says, if Mr. Bond just randomly guesses, then he should get the test correct 50% of the time. You know, 50-50. And that's the law of large numbers says that's what it's going to end up at. Well, he took a sip 30 different times, and he guessed correctly on 12 out of those 30. But I want to talk to you about the tail on this. Here's the null that the proportion he gets right is 50% of the time. If he gets a sample up here, way high, then it is clear that what? He can tell the difference, and he gets that a whole bunch right. Okay, he can tell the difference. He gets a lot of them correct. Now, down here, what's this? He gets a very large proportion of them, like maybe almost all of them, what? Okay, if you're getting a ton of them wrong, so a lot wrong, then you actually are distinguishing something here. You just have the answer mixed up in your brain. Let me put it in your terms. How many of you think you can tell the difference between Pepsi and Dr. Pepper? Okay, way me, yes, big time. So what if you took 30 sips and you got 29 out of those 30 wrong? It's because you could tell the difference between the things. You just had the definition mixed up. You were thinking that Pepsi tasted like Dr. Pepper and Dr. Pepper tasted like Pepsi. So getting it way wrong also means that your tongue was distinguishing a difference. It just had the flip of the answers reversed. So this also would mean that he can tell a difference. So that is why this problem is a two-tailed problem. So when your null is that it's 0.50, meaning he can't tell the difference. The alternative is going to be two-tailed. Okay, so there you go. So you're going to finish that. The next one, you're going to finish that. Those two problems on the homework and your warm-up. All right, I need to stamp you for your last night's homework, your 4 problems there.